Hello and good evening, good morning, good afternoon, wherever it is that you are. And we are going to be looking at reaction mechanisms. And the approach that we are taking is being given a proposed mechanism. We will determine what is the rate law consistent with that mechanism. Okay, so I'm going to start out by giving you an overall chemical reaction. All right, so for the reaction, okay. So this is a reaction that is in the gas phase. However, iodine, at room temperature, it is a solid. However, it is volatile enough that you can actually get some iodine vapor. Okay, and this iodine vapor can react with hydrogen in the gas phase, and these two can react together and give two hydrogen iodide molecules in the gas phase. Okay, so one might look at this chemical reaction and just think, well, these two molecules can collide into one another and then just directly form two of these HI molecules. Okay. However, that is not the mechanism. That is not in real time how these molecules collide to give these products. All right, so there were quite a few experiments done. This is many, many years ago. And they realized that there were observed these free iodine atoms. Okay, so they observed these spectroscopically, and they confirmed indeed they were these lone iodine atoms that were observed in the gas phase during the course of this reaction. So that got them thinking, and they proposed the following mechanism. Now, I wasn't there. It's probably figured out before I was born, but there may have been quite a few different mechanisms. Let me just turn this into proposed mechanism. And this one has survived the test of time. Okay. So in this proposed mechanism, there are 3 steps. Okay, so step 1, the iodine vapor. Like I said, most of it stays in the solid phase, but some of it does vaporize. And what can happen is there is a fast equilibrium that occurs, and this iodine molecule dissociates to give 2 iodine atoms separate from one another. And this equilibrium is quite fast. Okay, so that's something we want to acknowledge in any proposed mechanism. Okay, and we can also designate the rate constants in the forward direction. I'm going to bring out my other pen. And this is a little bit thinner, finer, so it can fit in here. Okay. So this is our rate constant K1, and the reverse of it is rate constant K to the minus 1. Okay, then what happens? So next, one of these iodine atoms can collide with a hydrogen molecule. All right, so here is a gas phase iodine atom colliding with a hydrogen molecule. And again, we have a fast equilibrium going on here. And this forms a very interesting molecule, not seen very often, H2I. And again, this happens at a very fast rate. Now we just use the terms fast and slow as a comparison for each of these elementary steps. And we need to know which one is going to be the slowest step, because that is the one that is going to designate what the rate law is. Okay, so this is a pretty unstable molecule, and so the scientists who proposed this particular reaction mechanism, they then proposed in step 3 that this H2I, it's pretty reactive, can collide with one of those free iodine atoms and directly form, notice how this is not a fast equilibrium, 2 HI, hydrogen iodide molecules. This reaction occurs relatively slow. Okay, so let's now designate the rate constants for step 2. We can say that the rate constant in the forward direction is K2. The reverse direction is K minus 2. And step 3, going in the forward direction, K3. So we want to identify each one of these rate constants because each one of them is different from the other ones, and we can use these to our advantage when we are trying to figure out what is the rate law. So that's really the big question here, because whoever proposed this mechanism, they needed to make sure that the rate law that is consistent with this particular mechanism is consistent with the experimental data. Okay. So when you are proposing a mechanism, first thing you do is you make sure that each of these elementary steps adds up to give the overall chemical equation. Otherwise, you cannot move forward if that is not true. Okay. Another thing you want to do is make sure it's a reasonable mechanism, that you never have 4 molecules that are colliding to create something else. The probability of 4 molecules colliding is so low, it is infinitesimally slow or unlikely. So 4 molecules hitting. It is possible 3 can hit, but 2 molecules colliding is very possible. And 1 molecule breaking apart is also very possible. This is called a unimolecular elementary step. Just 1 molecule, in this case breaking apart. Here's a bimolecular step. 2 molecules colliding to form products. Here, 2 molecules colliding. Bimolecular elementary step. And we also make sure that the proposed mechanism has information that's consistent with the experiments. So in this case, it was observed that there were iodine atoms floating around during the course of the reaction, and that indeed is shown in step 1. So those are a few of the grand indicators that you have a good proposed mechanism. But it does need to have a rate law that is consistent with what is observed experimentally. Okay, must match experimental rate law. The experimental rate law is a good conversation for a different video. And I think I do have a video on that, or I need to make one. Perhaps one that has the method of initial rates or using integrated rate equations to solve problems. But here, what we want to do is we want to do an assessment of this mechanism and make sure that we know what the rate law is so that we can match it with that which was determined experimentally. So here is our focus. The rate law must be consistent with the rate determining step, which is the slow step. Okay, also known as rate determining. So, what we can do is, because step 3 is an elementary step, we can write a rate law directly from this elementary step. And the reason why we can do that is because elementary steps show us what is actually happening between the molecules. So the rate will depend on what is the concentration of H2I and what is the concentration of I. Whereas you cannot write a rate law directly from an overall equation because you don't know what the mechanism is. So you can't say, will the mechanism necessarily depend on concentration of I2 or H2 because you haven't verified the mechanism. Okay. So with that, we can write that what I call a mini rate law. I say, let's look at the rate of just step 3 alone. I'm purposely choosing this because it is the slow step. And the overall experimental rate law must be consistent with the slow step for this mechanism. So we choose the slow step and we write out the rate law. Step 3. Rate 3 equals the rate constant, K3, for this step times concentration of H2I times concentration of I. So notice how I wrote these directly from this elementary step. Okay. And now we look at this and we say, is this rate law accurate? And is it written correctly? And when I say correctly, I mean that rate laws follow rules. And one of those rules is no intermediates allowed. Okay, what is an intermediate? Well, an intermediate in a reaction mechanism is any species that appears in an elementary step for just a brief moment and then disappears in a later step. In this particular mechanism, we've got two that show up in one step. One of them is consumed in step 2. Another one is consumed in step 3. But they do both disappear. They do not appear in the overall chemical equation. Okay, so they appear and then they disappear. And iodine is one of those intermediates. This is not allowed in a rate law. Same with H2I. It's an intermediate, not allowed to exist in the rate law. So this doesn't mean that this is incorrect, but it does mean it's not written in a form that is allowed. But the good news is that we can do some substitution and we can identify what is the concentration of H2I in terms of I and H2 because of this fast equilibrium. So let me show you this trick that you can use. We are going to use fast equilibrium for step 2. And what we are going to acknowledge is that because this is equilibrium, it means that the rate in the forward direction equals the rate in the reverse direction. So in other words, rate 2 is equal to, that's supposed to be a 2, is equal to the reverse direction, or in other words, we could say rate minus 2. So how would we write rate 2? Well, that's the rate law in the forward direction, which would be K2, right, the rate constant, times concentration of I times the concentration of H2. Similarly, for the reverse, we would now use K minus 2, rate constant, and this would be multiplied by what is over on the side, H2I. And now we consider, how could we rearrange and use this equation to substitute into H2I? All right, so let's solve for H2I essentially. We can do that by dividing both sides by K minus 2. So that would give us K2 divided by K minus 2 times I times H2. Yes? Okay. So now that allows us to grab this other color. We can now substitute this H2I into here in our rate law. So let's take a look at what that would look like. That would be the same as saying rate 3, rate law for the slow step, rate 3 equals K3 times H2I, but now we're going to put all this in instead of H2I. Okay, so let me write this out. Rate 3 equals, we've got now, I'm going to put all the rate constants together at the front. Okay, so that's K2 and K3 are in the numerator. K minus 2 in the denominator. It is convention to keep all the rate constants together at the beginning. All right, and this would be multiplied by I and H2. Okay, that looks a little bit better. Oh, we need to have the other I there, sorry. I thought something looks a little wrong here. Okay, I got it. Okay. So we notice here that we have these two I's, and we can combine those together. So why don't we do that? Bring this up onto the sheet. K2, K3, K minus 2. Okay, look at what we can do here. We could write this for H2 and then combine those two I's together. All right. This is still not perfect, is it? If we assess this rate law, we still have a problem. It's fine having all these constants together. That's no problem at all. It's fine having a reactant show up in the rate law. No problem at all. You can also have products, all right? But what you're not allowed, no intermediates. And we still have these intermediates here. Okay, so guess what we get to do? We are going to use the fast equilibrium trick that we did for step 2 again, but now for step 1. And we can see almost right away we need to substitute out these iodine atoms that are intermediates. They're the iodine atoms. There's 2 of them right there. And that's going to allow us to substitute it out in the form of I2. And if you didn't follow that, let's do it. That will help you see better. Okay, so now use fast equilibrium, but now it's for 1. Can only do this when there's an equilibrium. Okay, so this whole idea here is that we are acknowledging that the forward rate, now it's for step 1, equals the reverse rate. And if we write out, how would we write the rate law? According to step 1, it would be K1 times the concentration of those reactants, which in this case are the I2 molecule. And then what about the reverse? This is now taking 2 of these iodine atoms reacting together with the rate constant of K minus 1. All right, so there's our K minus 1 rate constant. And there are 2 of those iodine atoms, so we can square those. And look, this is looking fabulous because see how this is the part of our rate law that's not allowed, And we are so close in determining a way to reflect what does this equal in terms of one of the reactants. So all we have to do is divide both sides. I'm getting low on the paper here. Divide both sides by k minus 1. Alright, k1 divided by k minus 1 times I2 molecule. Okay, perfect. We are so close. Okay, why don't I move this over here? And so at this point, we can take all of this and we can bring it up into this rate law. So let's take our k1, our k minus 1, and cluster it together with these other rate constants. So we end up getting k1, k2, k3, all divided by k minus 1, k minus 2, and then we can substitute in the I2 and we have our H2. So we are nearly complete. The only thing left to do is to simplify this rate law. Okay? And the way we do that is we say, all right, hey, we've gotten to the point where we can just report this as the rate of the reaction. Because rate 3 was for the slow step. And so we know the overall reaction can only ever be as fast as the slow step. So we can just call it the overall rate. And all of these are constants, so we can roll them into one constant. And then we have concentration of H2, concentration of I2. And we did it. There is our overall rate law. Okay, not trivial, right? Let's see if I can get all of this on here. Okay, very close. Not quite. But we can see here with this 3-step mechanism, we had to go through 2 of these substitutions. In both cases, because they were equilibria, step 1 and step 2, we were able to do this fun little equilibrium trick to be able to substitute out those pesky intermediates that are not allowed in the overall rate law. And ultimately, there's our rate law. So I hope that is helpful for you in your fun times. I can say that because I do love reaction mechanisms. But your journeys through learning about reaction mechanisms and how to determine a rate law from them. This particular problem was on the more complex side. So don't be surprised if you were asked for a rate law for a 1-step mechanism or 2-step one where it's pretty straightforward and where you don't need to do any substitution when you're first learning it. But as you continue and it gets a little bit more complicated and nuanced and complex, then you will begin to have a chance to do substitutions like this. Another caveat I will give is that this particular technique is one that is most often taught in general chemistry. But there can be points when you need to bring in something called the steady state approximation. And if you do get into that, that is, it's a larger umbrella. So it works for more different kinds of situations. And I do have a video on that, on using the steady state approximation for inorganic complexes. If you are curious about that, you can find that video. So, all right, well, I hope this was helpful for you. Thank you so much for the requests that I've been getting for what topics to talk about. I have a long running list, so I just keep chugging through them, and I am here to help all of you, and I hope it is helpful. So thank you so much, and do let, if you know people this might be helpful for this channel, let them know that I'm here. And it's all about very, very relaxed way to absorb chemistry. And generally speaking, this is usually around AP chemistry level in high school or general chemistry level in college, but sometimes I do topics that are a little bit more advanced as well, just depending on what all of you need. So you can always let me know. All right. So thank you again so much, and I will see you next time.